Okay, so bond enthalpy. Bond enthalpy. Okay, so if we take this chemical reaction, very simple chemical reaction, if we take some hydrogen gas and some oxygen gas, and we provide a little spark, a little bit of energy, a light to get the reaction started, then it makes a very loud bang, and it produces water. Okay, it's an exothermic reaction, so the enthalpy change for this reaction is exothermic in kilojoules per mole, and it makes a really loud bang. Okay, we just need to balance the chemical equation. So we've got one oxygen, but so we're going to need to put 2 here, so that we've got 2 oxygens. We've got 4 hydrogens, so we need to put a 2 here. Okay, so it's an exothermic, produces energy, and it's very loud. Okay, now if we were to draw the enthalpy profile diagram for this reaction, if we were to draw the enthalpy profile diagram for this reaction, so enthalpy, progress of reaction, okay, it's an exothermic, so we've got the reactants, just put the reactants on the line, and then the products, because it's exothermic, the products are going to be lower enthalpy than the reactants, and the change in enthalpy from the reactants to the products, the change in enthalpy is delta H. Okay, and then we always, normally when we draw enthalpy profile diagrams, we always go like this and draw like this, you see, and then that's the activation energy, the minimum energy needed to start the reaction. Okay, but what does this actually mean when we draw this like this? What does it actually mean? In order for this reaction to happen, what needs to happen first? What needs to happen first in order for hydrogen and oxygen to make water? Okay, so if we look at it simply like that, we go, okay, well, what needs to happen first? So if you've got your reactants, and you've got, remember that oxygen is actually a double bond. It goes around as a diatomic molecule. That's what oxygen looks like. And hydrogen is a diatomic molecule, and that's what that goes around looking like that. Okay, just a single bond. So if you have got 2 hydrogen molecules and an oxygen molecule, this is enthalpy against progress of reaction, and that's your starting material. Okay, what's the first thing? And I've just drawn it out so you can see the bonds. What's the first thing that needs to happen? The bonds have to break. Okay, and it's really difficult. If you think about breaking, if I want to break this pen, it's really difficult to break something, and it needs energy. It's positive, it needs energy. So it needs energy to break the bonds. Okay, so energy needed to break bonds, to break the bonds. Okay, now if you break the bonds, then what are you left with if you break all those bonds? You're just left with a single atoms. So you'd have 4 hydrogen atoms, and you'd have 2 oxygen atoms. You're just left with single atoms if you break all the bonds, and that needs energy, and that is a positive enthalpy change. And then in order to get the product, which remember is 2 water, the product is 2 water molecules. So we're going to draw the product down here, and you know the shape of water molecules. 2 water molecules. In order to get the product, all these single atoms are going to have to join together, and they're going to have to form new bonds. Okay, so they need to form bonds. Now, if breaking bonds, energy is needed, then the opposite, when you form bonds, energy is released. So this is a negative value. Okay, so breaking bonds is positive and forming bonds is negative. And then the overall enthalpy change is just a difference between them. Okay, in this example here, you can see that more energy has been released on forming the bonds that is needed to break the bonds. Okay, so that's really important. Let's just write that down. More energy, sorry, that's not been very well. More energy is released when forming the bonds. So when more energy is released when forming the bonds than is needed to break the bonds. Okay, so more energy is released, bigger arrow, more energy is released when when forming the bonds that is needed when breaking the bonds. And this is overall an exothermic reaction, because it means, because if we put pretend numbers in, if we just put some pretend numbers in, like pretend that this was 100 kilojoules per mole, pretend, okay, that's a pretend number, pretend this was 150 kilojoules per mole, okay, you can see that this is just 100, this is a minus 150, so the enthalpy change will just be 50 kilojoules per mole. Okay, sorry, it'll be minus because it'll be 100 and minus 150, which is a minus 150 kilojoules per mole. Sorry, minus 50. Minus 50 kilojoules per mole. Okay, but those are just pretend numbers. 100 minus 150 is minus 50 kilojoules per mole. Okay, anyway, this part here on the enthalpy profile diagram, this bit here on the enthalpy profile diagram, okay, is when we're going like this, we're forming single atoms and then we're coming back down to form the bonds. We break the bonds and then we make the bonds. Breaking bonds needs energy, making bonds releases energy. Okay, so that's bond enthalpy, but we need a little bit more information. Right, we need definitions. That's basically what it is, but let's get some definitions written down. Okay, you do actually need to know the definition for bond enthalpy. All right, so bond enthalpy is the enthalpy change. This is a definition. Bond enthalpy is the enthalpy change. For breaking enthalpy change for breaking 1 mole of a given bond. It's normally a covalent bond in the gaseous state. And this is really important in the gaseous state. Okay, enthalpy change for breaking 1 mole of a given bond in the gaseous state. So if I said to you, write an equation to represent the bond enthalpy of the hydrogen, the bond in hydrogen. Okay, if I said to you, write an equation to represent the bond enthalpy of hydrogen, so you would write, so the bond enthalpy of hydrogen, we're going to break that bond and we're going to get 2 single hydrogen atoms. Okay, that has a positive value of, it's actually plus 436 kilojoules per mole. You don't need to remember these values, you just need to remember it's positive. Okay, if I said to you, the bond enthalpy of the oxygen, or you can write it, you don't have to write it like that, you could just write H2 like that, you could. Okay, let me just show you this table. So in an exam you'll be given a table like this. Okay, so I hope you can see this table, and it's got the bond, and this the energy needed to break all of these bonds, okay? Right, you can see here though it says the word average bond enthalpy, because the problem is that each bond has a slightly different strength. So if we take this compound here, okay, with all the hydrogens on, okay, can you name this compound? Can you name it? 1, 2, 3, 4, 5 pentane, and then 1, 1, 2, 2 methyl pentane. Okay, now there's lots of CC bonds in here. CC bond, CC bond, CC bond. Now the strength of a CC bond in the table here needs this much energy to break a CC bond. But this is an average bond enthalpy because each CC bond, depending upon its environment, okay, depending upon its environment, each bond will have a slightly different strength. So this is just an average for all the CC bonds. It's an average value, but each bond would actually have a very slightly different strength. But sometimes we use the word average. So if you're asked for the definition of average bond enthalpy, then all you need to do is just change slightly your original definition. If you're asked for average bond enthalpy, then you just need to say is the average enthalpy change for breaking 1 mole of a given bond in the gaseous state. Okay, back to this table again. If you're given a table like this, you don't need to remember the specific numbers. You do need to know that this table is all about bond breaking. Okay, so you do need to know it's all about bond breaking, and that's why all the values are positive. You do need to know if you're asked about bond making, then all you need to do is change the sign. Okay, so if you're asked about bond making a bond, forming a bond, then you just change the sign. And also on this table you should be able to recognize which bond is the strongest bond, which bond needs the most energy to break. So the strongest bond is going to be the bond that needs the most energy to break, which is that. You can see it's a double bond as well. Okay, so that's the strongest bond because it needs the most energy to break it. Okay, whereas something like, what's the weakest bond? Just going through the weakest bond. So this is the weakest bond because it in this table because it needs the least energy to break it. Okay, right, so what we need to do is have a go at some calculations. So let's have a go at some calculations. I've got some written up here. Let's start with our simple example that we started with. Okay, so we're going to work out, so the job is, what we need to do is we need to work out the enthalpy change for this reaction. Okay, that's what we're trying to work out. So we're not going to do an experiment. We're not going to use enthalpy cycles. We're going to work out the enthalpy change using bond enthalpy. Right, now the method you use, if you use this method, you will always get the right answer. Okay, you go from the arrow like this, you go to 2 columns, you make a list of bonds broken on this side and bonds made on this side. Okay, you make a list. If you follow this method, you will always get the right answer. Okay, now if you can't see the bonds very well, it's a really good idea just to draw them out. So you're going to have 2 hydrogen molecules, 2 hydrogen molecules and an oxygen molecule. That's what we've got on the left hand side. Okay, so using the table, we use the table to help. Okay, the table's just down there. Right, so, and it's in your textbook as well, the table's in your textbook as well. So we've got a hydrogen bond, but we've got 2 of them. Okay, 2 of them. So we're going to break 2 of these bonds, these HH bonds. When I say hydrogen bond, I don't mean the intermolecular force. I mean just the 2 of the HH bonds. And we look at the value on the table, make sure you get the right one. and the value is 436. So 2 times 436. Okay, we're also going to break the OO double bond, and that value in the table is 497. So 497, and then you total that side. So you add everything up on that side. Okay, and when you do that, what does it come to? It comes to, when you total everything up on that side, it comes to 1369 kilojoules per mole, right? That's in kilojoules per mole. And you do exactly the same on the other side. Okay, so bonds made. Draw your water molecule out so you can see it, and you remember you've got 2 of them. You've got 2 of them like that. Okay, so you've got 2 of them. So you're breaking 1, 2, 3, 4. You're breaking OH bond, but you're breaking 4 of them. Okay, so make sure you're working nice and clear. You will not make any mistakes. Okay, OH bond is 463. So I'm going to go 4 times 463, and there's nothing else. So I'm just going to total that side, add it up, and it comes to 1852. 1852, right? Kilojoules per mole. And then you go, okay, right, so you go bond breaking needs energy plus bond making releases energy minus. So when I work out the enthalpy change for this reaction, I go, well, this, I take this 1369 and I add together plus I add together the other number, and it gives me the answer, which is minus 483 kilojoules per mole. And that's how much energy, the enthalpy change when you do this reaction. So it's not using an enthalpy cycle, it's not using an experiment MC delta T, it's using bond enthalpy. Okay, got another example for you to try. So when you can try this yourself and then check your answer, you've got to find the enthalpy change for this reaction. Okay, find the enthalpy change for this reaction. So this is just a combustion of methane, complete combustion of methane. All right, use exactly the same method again. I'm trying to find this enthalpy change. Draw your 2 columns. So bonds broken on this side, bonds made on this side. So pause the video, give it a go, and then check your answer in a second. Okay, so I'm going to draw it out so I can see really clearly. I've got methane, which are 4 CH bonds. I've got 2 oxygen molecules, like that, so I can see everything very clearly. So I'm going to break the CH bond, and that's 1, 2, 3, 4. I'm going to slice it like that, break them. 4. I'm going to break 4 times CH as a value of 413. 4 times 413. Okay, 4 times 413. And then there's oxygen, double bond oxygen, but we're going to break 1, 2 like that. I'm going to break 2 of those, and that is 497. Put the value there. Total, what that side equals, and it should come to 2646 kilojoules per mole. 2646. Do exactly the same on the other side. Now be careful here. Carbon dioxide. You've done this with Paul. Carbon dioxide is like this. Okay, and then don't forget your water molecules, or 2 water molecules, 2 of them, like that. So it's always wise to just draw it out. So you're going to break 1, 2. You're going to break C double bond O. You're going to break 2 of them. And C, remember, C double bond O is the strongest bond. C double bond O is 805. You're going to break 1, 2, 3, 4. You're going to break OH. You're going to break 4 of them. OH, where's OH on the table? 463. And then total that side, and it comes to 3462. Okay, and then you say, okay, you go, right, bond breaking is plus bond making is minus releases energy, and then just simply add them together. The enthalpy change equals, so you've got 2646 and add the other one, minus 3462, and you get your answer on your calculator, which is minus 816 kilojoules per mole. Kilojoules per mole. Okay, and there's the answer there. So did you get the right answer? Well done if you got the right answer. Right, before we finish, okay, we just need to do one last thing, okay? If you calculate this value for this enthalpy change of combustion, it comes out as minus 816, okay? But if I was to look it up in the data book, right, so if I was to look it up in the data book, in that reference book, that value actually comes out as minus 890 kilojoules per mole. Okay, so calculated value is that, but when we actually look it up in the data book, the actual proper value, the true value for this enthalpy change is minus 890. So why is the calculated value not accurate? We did everything right, we did the calculation right, but why is it not accurate? Okay, so there's two reasons. Okay, can you guess what the reasons are? First reason, we're using average bond enthalpies. We're not taking the exact bond enthalpy for every bond. Average bond enthalpies are used. Average bond enthalpies are used, and that is why it's not accurate. We're not taking it for exactly each bond. And then second, we're assuming that everything is in the gaseous state. Remember with the definition, bond enthalpy, bond enthalpy is the enthalpy change for breaking 1 mole of a given bond in the gaseous state. So bond enthalpy assumes that everything is in the gaseous state. But in this example, okay, I know it looks like everything's gaseous, but for the enthalpy change of combustion, that shouldn't really be gaseous. That should be liquid, shouldn't it? For the standard enthalpy change of combustion, because everything needs to be in their standard states. So another reason why it's not accurate is that bond enthalpy is for gases only, and we're using it for something that's not gases. It's not gaseous. It's for gases only. For gases only. Okay, it's for gases only.